Welcome back to G Fun Facts Online, where we dive deep into the science and technology shaping our future. Today, we are going to explore a topic that feels like it has been ripped straight out of a science fiction novel, yet it is currently being engineered in laboratories all around the world. We are talking about the history and the future of display technology, specifically a new era that promises to erase the distinction between the device you hold and the materials that make up your world. This is the story of the Stretchable OLED display. To really appreciate where we are going, we first need to look at where we have been. The history of display technology is essentially a history of liberation. It has been a relentless pursuit of freeing the image from its physical constraints. Think back to the cathode ray tube. It was heavy, bulky, and it anchored the image to a specific corner of the room inside a deep glass box. Then, we liberated the image from that bulk, flattening it into the liquid crystal display, or LCD. That was a massive leap. But we didn't stop there. We then liberated the screen from its backlight, allowing the self-emissive brilliance of organic light-emitting diodes, or OLEDs, to take over. This gave us thinner screens and perfect blacks. Recently you have seen the next phase of this liberation, the liberation from rigidity itself. We now have foldable phones and rollable TVs that bend the rules of form factor. But here's the secret that display engineers know. Flexible was never the final destination. It was merely a warm-up act. The true holy grail of display engineering is not a screen that merely bends, but one that behaves like skin. We are talking about a display that can warp, twist, deform, and stretch. We want a screen that can expand its surface area by 20%, 50%, or even 100% without breaking and without losing its image quality. This is the era of the stretchable OLED display. Achieving this requires a total reimagining of materials science, mechanical engineering, and manufacturing processes. It forces engineers to do something that physics fundamentally hates: take brittle, high-performance semiconductors and make them elastic. To understand the magnitude of this challenge, we have to start with part 1, the physics of the impossible. You must first appreciate the inherent fragility of a standard OLED pixel. A conventional OLED is a sandwich of organic thin films. You have hole transport layers, emissive layers, and electron transport layers, all placed between two electrodes. These layers are nanometers thick and are usually deposited on a glass or rigid plastic substrate. The materials involved, particularly the inorganic electrodes like indium tin oxide and the encapsulation layers like silicon nitride, are ceramics or metals. They are stiff. If you pull on them, they do not stretch, they crack. A strain of even 1% is often enough to fracture a standard transparent electrode, severing the electrical connection and killing the pixel instantly. Now, compare that to our goal. Stretchable displays must withstand strains of 20% to 50% or more. To bridge this massive gap between a 1% tolerance and a 50% requirement, engineers have developed two rival schools of thought: geometric engineering and intrinsic engineering. Let's start with the first approach, geometric engineering, often called the island bridge architecture. This is the most mature approach to date and is the one used in recent high-profile prototypes, like LG Display's 2024 unveiling of a 50% stretchable panel. The philosophy here is simple: if the components can't stretch, don't stretch them. In this paradigm, the active components, meaning the OLED pixels and the thin film transistors that drive them, are kept rigid. They are clustered onto tiny, microscopic islands made of stiff polyamide. These islands are then isolated from one another, floating in a sea of soft, elastic material like PDMS, which is a type of silicone. The magic lies in the connections. You cannot simply run a straight wire between these islands. It would snap immediately upon stretching. Instead, engineers use serpentine interconnects. Imagine a spring. A straight metal wire is stiff, but if you coil it into a spring, it becomes stretchable. Serpentine interconnects work on the same principle, but in two dimensions. They are metal traces, patterned into fractal, S-shaped, or horseshoe curves. When the display is stretched, the islands move apart, and the serpentine wires simply uncoil, effectively straightening out without actually stretching the metal material itself. The strain is absorbed by the geometric change in shape, not by the deformation of the atomic lattice. However, this geometric design comes with serious engineering challenges. The biggest downside is the fill factor, or the dead space. Since the interconnects need room to uncoil, you cannot pack pixels tightly together. This lowers the resolution. Early prototypes looked like screen doors because of the gaps. Modern engineering combats this with multi-layer wiring and hidden interconnects that tuck under the pixel islands, pushing resolutions toward the 100 ppi mark. Another geometric trick is using kirigami structures. Inspired by the Japanese art of paper cutting, some advanced substrates are pre-cut in specific patterns. When pulled, the substrate tilts and rotates the islands out of plane, turning tension into torsion, or twisting, which many materials handle better than direct tension. Then there is the issue of stress concentration. The critical failure points are where the soft, stretchy substrate meets the hard, rigid island. This interface is prone to peeling apart, Engineers use stress relief layers, which are intermediate materials with a stiffness halfway between the rubber and the plastic, to smooth out the mechanical gradient. Now let's look at the second approach, intrinsic engineering. While the island bridge method is a clever mechanical hack, the pure engineer's dream is intrinsic stretchability. This involves synthesizing entirely new electronic materials that are inherently elastic. Imagine an OLED stack where every single layer, the anode, the cathode, the light emitter, and the encapsulation, is made of rubber. You could stretch it, twist it, and poke it, and it would just glow. This is the frontier of polymer chemistry. To explain this, we use the noodle theory of conductive polymers. Standard conductive polymers are like dried spaghetti, stiff and brittle. If you bend them, they snap. Intrinsically stretchable polymers are like cooked spaghetti. They consist of long molecular chains that are entangled but can slide past one another. To conduct electricity, polymers usually need a conjugated backbone of alternating single and double bonds, which provides a highway for electrons. Unfortunately, this rigid backbone usually makes the plastic stiff, so chemists are now designing rod-coil block copolymers. They insert soft, non-conductive coil segments like polyethylene in between the rigid conductive rod segments. The soft coils act as molecular springs, allowing the rigid rods to slide and rotate without breaking the electrical pathway. Another technique involves adding external plasticizers. These are molecular lubricants added to the polymer mix. These small molecules sit between the polymer chains, increasing the free volume and allowing them to move more freely. Recent breakthroughs have even used fluid-conjugated plasticizers, which are liquids that actually help conduct electricity while softening the material. But what about the electrodes? Even the best conductive polymers often have too high a resistance. The solution is liquid metal, specifically eutectic gallium indium, or EGAN. This is a metal alloy that is liquid at room temperature. It conducts electricity like a copper wire but flows like water. By encapsulating microchannels of liquid metal within a rubber substrate, engineers can create electrodes that remain perfectly conductive, even when stretched to 300% of their original length. University of Chicago researchers recently made headlines with a brittle-to-elastic breakthrough using this concept. They discovered that by alloying aluminum with specific elements and depositing it on a specialized polymer, they could make the metal layer crackle into millions of microscopic plates that slide over each other. It maintains conductivity like chainmail armor rather than a solid shield. Now, moving on to part 2, the 3 pillars of engineering hurdles. Building a stretchable OLED is a weakest link problem. If the substrate stretches but the encapsulation cracks, the device dies. Let's talk about the encapsulation nightmare. OLED materials are notoriously divas. They degrade instantly in the presence of moisture or oxygen. A single molecule of water can kill a pixel, creating a dark spot that grows over time. For rigid displays, we use glass to seal them, but you cannot stretch glass. So engineers are developing hybrid dyadic barriers using a tortuous path concept. Imagine a brick wall. The bricks are rigid, impermeable inorganic particles. The mortar is a soft, stretchable polymer. Water molecules trying to get in face a maze. They have to wiggle around the bricks, through the polymer, and find the next gap. Using a manufacturing technique called atomic layer deposition, engineers lay down these barrier films one atomic layer at a time. Some cutting-edge research even uses polymers that can self-heal microcracks. If the barrier is stretched too far and a fissure opens, the polymer flows to seal the gap, maintaining the hermetic seal. The second hurdle is the backplane dilemma. You need a switch to turn each pixel on and off, which is the thin film transistor, or TFT. Most prototypes use rigid silicon TFTs sitting on the islands, but the future lies in organic thin film transistors, or OTFTs. These are transistors made of plastic. While historically slower than silicon, their performance has improved drastically. Researchers have even found that compressing the crystal lattice of organic semiconductors can actually improve their speed by reducing molecular vibration, turning mechanical stress from a bug into a feature. The third hurdle is the resolution versus stretchability trade-off. It is a zero-sum game. More serpentine wiring allows for higher stretchability but leaves less room for pixels. However, researchers at KAIST recently proposed a genius solution, the hidden active area. They designed a 3D structure where the pixel material wraps around the edges of the island or is tucked into the folds of the substrate like a pleated skirt. When the display is relaxed, these hidden areas are folded away. When you stretch the display, the pleats unfold, and the hidden pixel area is revealed. This maintains a high fill factor regardless of the stretch. Now, let's look at part 3, manufacturing. You cannot make stretchable displays in the same factories that make your TV. Standard fabrication relies on vacuum chambers and high temperatures that would melt the delicate elastomeric substrates. This is where inkjet printing becomes the hero. Companies like Cativa have pioneered massive printers that deposit OLED materials with microscopic precision. Printing is a low-temperature process, and it is additive, meaning you only put material where you need it. The printer nozzle jets tiny droplets of dissolved polymer into the specific island wells on the stretchable substrate. This avoids the need for shadow masks used in vacuum deposition, which are hard to align on a soft rubber sheet. Another technique is micro-transfer printing. Here, you fabricate the high-performance rigid components on a standard silicon wafer. Then, you use a soft rubber stamp to pick up thousands of these tiny chips at once and print them onto the pre-stretched rubber substrate. When you release the tension, the substrate snaps back, compressing the interconnects into little pop-up bridges. The ultimate dream is roll-to-roll manufacturing. Imagine a machine that prints displays like newspapers. A giant roll of rubber film feeds in, and layers of conductive ink and emissive polymers are printed on it. This would reduce the cost by orders of magnitude, moving stretchable screens from high-end medical devices to disposable items. So part 4, why do we need this? Why go through all this trouble? Because rigid displays force us to adapt to them. Stretchable displays adapt to us. Consider the concept of the fashionable cyborg or wearables 2.0. Current smartwatches are rigid pucks strapped to soft wrists. A stretchable display could be a wristband that is the screen, wrapping entirely around the arm and expanding as your muscles flex. Imagine smart clothing, like a running jacket with a display integrated into the fabric. It needs to survive the washing machine, the crumpling in a locker, and the stretching of the fabric. Only stretchable OLEDs can do this. Then there are automotive interiors. Car interiors are full of complex curves. Samsung and LG have conceptualized morphable dashboards. Imagine a smooth wooden surface. When you start the car, a section of the dashboard physically bulges out to form a button, with a display stretching over it to show the label volume. When you turn the car off, the button retracts, and the display snaps back to flat. But the most impactful frontier is the medical revolution, electronic skin. A stretchable OLED patch stuck to the skin could monitor wound healing. Using integrated sensors, it detects infection by checking temperature or pH, and uses the OLED to visualize the data directly on the bandage, showing red for danger or green for healing. It could also provide phototherapy, emitting specific light wavelengths to accelerate healing, wrapping perfectly around a joint to treat arthritis. Finally, let's look at part 5, the road ahead. We are currently in the prototype phase. The devices exist, but they are expensive, and yield rates are low. From 2026 to 2028, we expect the early adopters. You will see niche products like high-end sports gear or FDA-approved medical monitoring patches. By 2029 to 2032, we will likely see the successor to the foldable phone, the expandable phone. Instead of a hinge, which is a mechanical weak point, the phone will simply pull apart like a scroll, with the screen stretching to fill the space. By 2035 and beyond, market forecasts suggest a $500 billion industry. The cost of printing will drop enough that packaging becomes smart. A soda bottle might have a stretchable strip that glows when cold. Wallpaper could change color to match your mood. In conclusion, the engineering of stretchable OLED displays is a testament to human stubbornness. Faced with materials that want to shatter, we built microscopic bridges. Faced with molecules that want to stay rigid, we designed chemical springs. We are moving from an age of looking at screens to an age of living in them. The rigid black rectangle that has dominated our attention for 50 years is about to melt away, replaced by a digital fabric that is as flexible, organic, and resilient as we are. The future isn't just bright, it is elastic.